Welcome to our lecture online, and now we're ready to come up with the equation describing the particle inside a one-dimensional box. Now notice here that we have four particular situations, of course many more, but we're only considering the first four energy levels, n equals 1, n equals 2, n equals 3, n equals 4. If this was represented by a standing wave of a string, this is what the strings would look like. And so you can see that we can then calculate the wavelengths, lambda 1, lambda 2, lambda 3, and lambda 4. In the case here, lambda is equal to twice the length of the box because this is only half a wavelength. Here, lambda is equal to the length of the box. Here, lambda is equal to 2/3 the length of the box. And here, lambda is equal to 1/2 the length of the box. But if you then express it in terms of the quantum number n, indicating the energy levels, notice that in each case, lambda 1 is equal to 2 over n times L, lambda 2 is equal to 2 over n times L, lambda 3 is equal to 2 over n times L, and so forth, so that the wavelength in every single case is always equal to 2 over n times L. Notice that here n is 1, n is 2, n is 3, n is 4, so we'll always get the same expression for the wavelength for a particle inside a one-dimensional box. Now to find the energy of the particle, so now we have to go through our 6 steps, and I only have room for 4 on the board. We'll do the last 2 on the next video. On the first step, we're trying to find the energy of the particle. And remember, there's only kinetic energy here because there's no potential energy inside the box. The potential energy is infinite outside the box and 0 inside the box. Starting with the de Broglie wave equation, where lambda of a particle is equal to h divided by the momentum p, we can solve this equation for the momentum. So the momentum of a particle can be expressed as h divided by lambda. And the kinetic energy is known to be the momentum squared divided by twice the mass. This is really the same as saying 1/2 mv squared, no difference. And then if we replace p by h over lambda, this then becomes the kinetic energy is h squared divided by 2 times the mass times lambda squared. Now, for the particular situation, we're dealing with a box here. In the box, lambda is always equal to 2 divided by n times L, n being the quantum number representing the energy level. If we now replace the lambda in our equation here for the kinetic energy by what lambda must be for a one-dimensional box, we end up with this. And if we simplify it, it looks like n squared times h squared over 8 times the mass times the distance or the length of the box squared. So now you can see that the kinetic energy is indeed quantized, and it's going to depend on n squared, n being the quantum number representing the energy level of the box. The next thing we want to do is define the energy level for each, or the energy for each energy level, and we name that E sub n. So starting with h bar being equal to h divided by 2 pi, because notice here we simply have h, we don't have h bar, and we'd like to use h bar in the Schrodinger equation, so we want to make the translation that h can now be written as 2 pi h bar. If we replace the h here by 2 pi h bar, we end up at 4 pi squared h bar squared, and then of course if we simplify the 4 and the 8, we end up with n squared times pi squared h bar squared divided by 2ml squared. And if you then notice that this portion right here simply represents the energy of the first level when n equals 1, this can simply be written as n squared times the energy level of 1, which then allows you to find the energy of each particle at every energy level. For the n equals 1, we have 1 squared times E1, simply the energy of the first level. For n equals 2, we have 2 squared, which is 4 times the energy of the first level. For n equals 3, we have 9 times the energy of the first level. So that's how you determine the energy of all the various levels. The next thing we want to do is find and or define the wave number k. Again, we start with the definition that the momentum for a photon, and of course Schrodinger used that same concept to represent the momentum of a particle, can be expressed as h bar times k, which means that the wave number is now p, the momentum, divided by h bar. And if we square both sides, we can see that k squared equals the momentum squared divided by h bar squared. Since we know that the kinetic energy in this particular situation which is also the total energy of the particle, because there's no potential energy, can be expressed as p squared over 2m. Then if we replace the p squared by 2me, then k squared becomes 2me divided by h bar squared. And so now we have an expression for k. Simply take the square root, and that will then be the expression for the wave number. Now let's see here. I was going to make a comparison. Oh yes, I remember what I was going to do. All right, I'm going to use a different color now because I want to show the connection. Remember what this is the expression for. This here is represented by the energy at any particular energy level. So if we substitute this E here by this quantity here, we should be able to come up with the wave number k that represents our physical situation here, the one-dimensional box. So let's try to do that. We're going to substitute for E what E is equal to, which is n squared times pi squared h bar squared divided by 2ml squared. Now when we simplify things, because we can cancel some things out, we have a 2 here and a 2 there, an m and an m. We have an h bar squared and an h bar squared. Notice now that k squared is equal to n squared pi squared over l squared, or k can be expressed as n pi over l. And so now we have an expression for the wave number as a function of energy level for, of course, a one-dimensional box. Keep in mind that all these things only work for this specific situation, and if we have a different situation, we have to go through the entire process over again to come up with different values for those particular constants or for those particular variables. So here we have the wave number as a function of energy level is equal to n times pi divided by L. The next step now is we want to find an equation, a wave equation, describing what happens to a particle in a physical one-dimensional box. And since the Schrodinger equation, which is time independent, has now been reduced to just these two terms because the potential term is no longer there, we realize that when we take the second derivative of this, of the wave function, it generates the wave number squared. In other words, we can say that if we put 2m over here and h bar squared over here and put the negative over here, that the second derivative of the wave function equals minus 2m times e divided by h bar squared times the wave function. And we realize from going back over here that 2me divided by h bar squared is indeed equal to k squared, and of course, not forgetting the negative, we can then see that if we take the second derivative of the wave function, we should get minus k squared times the wave function itself. So what kind of function, when we take two derivatives, end up giving us the wave number? Well, the only options that we can think of is either the sine of kx or the cosine of kx. Take the derivative twice, you'll have to take the derivative of the angle. Twice you'll get a k factor out. Multiply together, it gives you k squared. And since the derivative of cosine is the negative sine, the derivative of cosine is the negative sine, you end up with the negative k squared times lambda, or times the wave function. Which means that either this function or this function is a good representation of the wave function that we can plug into the Schrodinger equation and end up with a good representation for the particle in a one-dimensional box. But there's a problem with one of these two. Notice that it requires that the wave function equals 0 at the boundary conditions. In other words, if I plug in 0 for x or L for x, I should get 0 back in the wave equation. And the cosine of 0 is, of course, not equal to 0. It requires the wave function to be 0 when we plug in a 0. Since the cosine does not do that for us, this is not a viable solution, and so therefore we cannot use that to represent the particle in a one-dimensional box. The only equation that allows us to do that then would be this equation, and that then is a good representation of the wave function for a particle in a one-dimensional box. Now, of course, the next thing we need to do is find out what the value of A is. We do that with normalization. And then finally, we can find the probability function that describes where we can expect to find the particle in a situation like this, in a one-dimensional box, depending upon what energy level the particle is at. So hopefully this clears it up for you in how to utilize the Schrodinger equation in a specific set of steps to come up with the wave equation and the probability function of a particle in a one-dimensional box.